Good evening. I'd like to welcome all of you to the first Frontiers of Science lecture of the year. There's a series of them, and if it doesn't show on the slide here, the folks out in the auditorium have the schedule for the rest of the year, so I hope you will come to the rest of them as well. The Frontiers of Science lecture series is the oldest and most popular lecture series on science on campus. It started in 1966, and we've had past speakers from practically every scientific discipline. We want to thank the College of Science and the College of Mines and Engineering Sciences and the Salt Lake Astronomical Society for sponsoring the Frontiers of Science lecture tonight. I should have introduced myself too. I'm Carlton Ditar. I'm chair of the Department of Physics and Astronomy, so I guess I had some connection to the speaker tonight. We also enjoy very much our relationship with the Salt Lake Astronomical Society. They help us out with our own star parties, and they also have star parties of their own. The Salt Lake Astronomical Society promotes astronomy in Salt Lake City and also the state of Utah. They go around to schools and run star parties there. They'll have star parties in Stansbury Park, where they have an observatory. And so what I'm going to do tonight, because of their participation and sponsorship, is to have Joan Carmen, who's the president of the Salt Lake Astronomical Society, to introduce our speaker tonight. She's in attendance in the audience here. She's an alumna of the university, actually studied political science when she was here, but she's been an amateur astronomer for more than 35 years. So please join me in welcoming Joan Carmen, who will then introduce tonight's speaker.
Thank you, Carlton. Yes, I'm the president of the Salt Lake Astronomical Society. We have combined for the last couple of years with the University of Utah Science Department to present lectures like this, and I think it's just really a symbiotic relationship. We work very, very well together, and I'm delighted to see so many people out here tonight. The subject for tonight is Pluto. I won't tell you whether it's a planet or dwarf planet or whatever. We won't argue those points. But it was discovered in 1930 by an amateur astronomer by the name of Clyde Tombaugh. He was looking for something that had a gravitational impact on Neptune. And he worked at Flagstaff, Arizona, and he found it within a few days. It was serendipity. But the moment it was found, it wasn't right. What he discovered was an object that its orbit, where you have the solar plane, this was tilted 30 degrees to the solar plane. It was initially thought to be about the size of Earth. Even then, it wasn't big enough to have the gravitational impact on Neptune that it was supposed to have. It would not fit into any category. As time passed, Pluto got smaller and smaller. In 1960, around the 1960s, Dr. Gary Flandreau here at the University of Utah realized that all the outer planets of the solar system would be in the same general part of the solar system. And if we sent a series of robotic craft out there, we could visit each one in turn. He went to NASA, he proposed this to them, and they jumped on board immediately. And they called it the Grand Tour. Unfortunately, NASA had to get funding from Congress. And Congress is not well known for scientific research, and so they started budget cutting. As it turned out, the Grand Tour ended up with 2 Pioneer spacecraft and 2 Voyager spacecraft that literally revolutionized our understanding of the outer solar system. Again, unfortunately, budgetary cuts, Pluto was not on that list. Finally, the Hubble telescope was launched in 1996, and it got some first few pictures of Pluto. It figured out that Pluto was round. It also found that there was some shading out there. It also realized that Pluto had its own satellites. Pluto has continued to defy any explanations. Fortunately, NASA finally got behind the program, and they went and got Congress to fund the New Horizons spacecraft. New Horizons was launched in 2006, and it took 9 very long years to get to Pluto. And it finally arrived last July. It performed flawlessly. The research team at Southwest Research Institute sat by and waited, and we have one of those research scientists here tonight to talk to us about what they have discovered with Pluto. Dr. John Spencer did his undergraduate work at Cambridge University in Britain, and when he gets up here, you're going to hear a very standard British accent. He has been in the United States since 1993, but he still has that accent. He can't quite lose it. But as I was talking to him earlier tonight, I've just discovered he is now a naturalized citizen of the United States of America. We got a good one. Dr. Spencer has been doing research mostly on the Galilean satellites, the moons that orbit Jupiter. But he joined the Southwest Research Institute in 2004. New Horizons was launched in 2006. And so he's been sitting there waiting patiently for 9 long years. And so now we get to hear what he has discovered about Pluto. Dr. Spencer.
Okay, first, let's see, do I have a microphone, or is there, oh, I guess I use this one here. Okay, I will lean forward. And I think if I hit input 1, they told me that will, aha, all right. So if we can have the lights down.
We want to get the lights turned down so they
Yes.
can see the slides.
Yes. I'm not smart enough to do that. Ah, all right, great. I will get started. So thank you all for coming. It's a great turnout, and glad to see other people as excited about Pluto as we are. I've given a lot of talks. One of the things I was doing for those 9 years, we weren't just sitting around twiddling our thumbs saying, oh, I wish we'll get to Pluto. We kept pretty busy, but one of the things I did was give a whole bunch of public talks about the mission, and this is the first one I've given since we got there, and we actually can talk about what we've found at Pluto, so I'm very excited to be able to talk to that. So as you know, the other thing if we can, is there a laser pointer or something here that I could get? I can manage without, but it would be nice to have. No? Well, anyway, it's no big deal either way. So yeah, this summer we flew past Pluto, which is a fairly astonishing thing. I still don't really believe it myself. And so thank you. This is a really, I better not point this in the wrong direction. Looks dangerous. So we completed the exploration of all the classical known planets. And how did we get to this point? I better start with some basics. You already heard a little bit of it. Where is Pluto? It's way out there. This is a simple diagram of the solar system. We are, okay, now I can use this thing. We are in here with the terrestrial planets, and here's the asteroid belt, And then there's Jupiter. And then you have to shrink down to see the rest of the... let's see. Let's see how this... Yeah. Okay. So, okay, can you... Right, how's the... Hello, hello, hello. Sorry, I don't know. Hello, 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 hello. Maybe a little bit higher. Hello, can you hear me now? No?
Okay, I don't know, sorry.
Yeah, all right.
Should have been done ahead of time, I don't know why it wasn't.
Yeah. I think it's just a matter of getting the level right. Maybe if I turn it down a little bit. How's that? No feedback? Yes, all right. Okay, where was I? Yeah, the outer solar system. So we have Jupiter now here. We're way down in the center of the solar system here. Then you've got the outer planets, and then Pluto's way out here. And for a long time, we thought it was out there on its own. We now know it's part of the Kuiper belt, which is like this enormous asteroid belt out beyond the orbit of Neptune. And I'll say a little bit more about that later. But for a long time, it was the only thing we knew out there. And how did we even find it was there in the first place? Well, as Joan mentioned, it was discovered by this guy, Clyde Tombaugh, back in 1930 at Lowell Observatory, where I used to work. So I feel this very strong connection with Clyde and the work he did. We used to walk our dog up to the telescope where Pluto was discovered, which is, you can go and visit there now. And he was hired specifically to look for a planet beyond Neptune. And the way he did this is there were photographic plates on the back of this telescope, and he would expose those and develop them, and then he would look at the same area 2 different times and look for anything that was moving. The stars don't move, but planets do. And so he'd have a plate like here, and he'd just painstakingly go over this, looking for anything that moved. And in here is Pluto. This is one of the images that he used to discover Pluto, and obviously you can't tell which it is. If I look at another image, so he would just spend days doing this and somehow not going crazy. But Pluto is moving in this field. If you were Clyde Tombaugh, you would have found it, but I don't know if you can see it, but just making it a little easier. He did not have this benefit. There it is. So he found this small point of light moving against the stars, and that's how the world learned about the existence of Pluto. I kind of like this. This is Clyde Tombaugh himself many years later, and you can see him moving too. Anyway, so we discovered Pluto in 1930. We didn't learn much about it except its orbit for many decades, but given advances in telescopes, we started to learn quite a lot starting in the 1970s and the 80s and beyond. And what we learned made Pluto seem very interesting. First of all, as Joan said, it's pretty small. It's actually about 1/5 the diameter of the Earth. But we learned it's a pretty exotic place. This is the best picture we had until this summer. That's with the Hubble telescope, the most powerful telescope we have, and you can see it's not very impressive. But we learned a lot from spectroscopy and other things. And we learned that Pluto had a very variegated surface. There's some areas that were very black, and maybe some sort of tarry hydrocarbon gunk. Bright areas with nitrogen frost and methane and carbon monoxide. But basically, we just made this up for what it might actually look like close up. In 1978, we discovered that it had a large moon, and so it's a double planet, kind of like the Earth and our moon. But Charon is even bigger relative to Pluto than our moon is relative to the Earth. And so you can see as Charon goes around, it makes Pluto wobble, and they're actually moving around a center of gravity that is outside the position of Pluto. So that's pretty unusual. And we think it probably formed in a giant impact that basically hit the original Pluto and knocked off a large chunk that formed Charon, which is exactly how our own moon formed. So we think there's a lot in common with our own system here. And it's very different from Pluto. We think it has dirty water ice, maybe some ammonia on its surface. In the last decade or so, starting in 2005, we found 4 more moons. These are much smaller. They may be 5 miles to 100 miles across. We didn't really know until we got there. So we have like this tiny solar system. The whole system would fit between our Earth and the moon, orbiting a double planet. So that's already a pretty crazy kind of place. We learned it had an atmosphere. We knew it was mostly nitrogen, just like the air in this room, but 100,000 times thinner than the air in this room. But methane and carbon monoxide as well. But we could tell this by watching Pluto pass in front of stars and watching the light from the star dim as it goes behind Pluto. So you can get pretty clever, and you can learn quite a lot from this, enough to kind of make a Pluto weather forecast. You might have a little snow. It's pretty darn cold. The day lasts for 3 days. So the sun would be up from Monday through Wednesday, and then it'll be down the rest of the week. It's a 6-day rotation period. The barometer reads pretty darn low. Methane humidity is about 100%. You can get methane snow, maybe. And you don't want to know about the wind chill. And as I've said, we learned about, in the last 20 years, that there are hundreds of thousands of other objects out there. Pluto is not an oddball out on its own. It's the king of the Kuiper Belt. There are lots of other objects out here, most of them much smaller than Pluto. But we actually know of some quite big ones. So this is Pluto and its moon Charon. Here is Eris, which is about the same size as Pluto and is much further away from the sun. And there's a bunch of others as well. So there's a whole slew of very interesting objects out there. And Pluto is the first one we've actually got to visit and see what it was like up close. So as Joan said, in the 1980s, we had the Voyager missions that visited Jupiter, Saturn, Uranus, and Neptune and found astonishing things everywhere they went. But they weren't able to go to Pluto. But about the time we got to Neptune with the Voyager spacecraft, people started thinking, you know, we really need to knock off this final planet that we haven't been to. We really need to have a spacecraft to go there too. And people started working on this back in the late 80s. And in the early 90s, I got asked to be part of a team to look at cameras for possible missions that might or might not fly. The early part of this process, actually, Clyde Tombaugh was still alive. And this is the leader, Rob Staley, who was the leader of one of these mission studies with Clyde Tombaugh and his wife, Patsy, in 1996. And Clyde died the following year and was not able to see the launch of the mission or his what Pluto was like up close, except that he did in a way, and I'll say that later. But anyway, after a lot of lobbying and a lot of help from people like you who just really cared about Pluto and wrote to Congress, NASA finally decided that, yes, they would fund a mission to Pluto. And in 2001, they asked anyone who wanted to fly a mission to Pluto, just write a proposal, tell us how you would do it, how much it would cost. You can have $500 million if you can do it right. Which is kind of amazing that anyone would make an offer like that. But I was part of a proposal led by Alan Stern here, who's been the driving force behind this for decades. This is our cover of our proposal, and we sent that in, and we just saying all the things we wanted to do, what our spacecraft would look like. We had a review panel visit. We built a cardboard model of our spacecraft, hoping that would impress the review panel. And then a few months later, or just a couple of months later, we got this amazing email from Alan Stern saying that, yes, we had been selected to be the team to build a spacecraft and send it to Pluto. So that was a good day. So we then had several years of designing this mission and figuring out just how all the bits were going to work. There was an awful lot of work went into that, but starting in 2004, we started construction, and I say we, I mean a bunch of engineers and I was part of the team, but the scientists were really taking a back seat at this point. It was an engineering effort. And here it is in fairly early stages of construction. You can see this kind of silvery gray bag here. This is the kind of anti-static bag that you get electronic components in, that you really worry about static electricity on spacecraft, and so it's often got wrapped in those kind of bags. The instruments that we put on the spacecraft that would tell us what Pluto was like when we got there, those, a whole set of them, here are a couple of them being attached to the spacecraft during construction. You can see a guy in a bunny suit behind here. This is a pretty small spacecraft. There's an ultraviolet instrument that's going to measure the composition, or is designed to measure the composition of Pluto's atmosphere. We had a couple of cameras, a black and white camera and a color camera. This is one of them here. This instrument also does double duty as an infrared spectrometer. That tells us what the surface is made of and makes maps of the composition of the surface of Pluto when we get there. There's plasma instruments to measure Pluto's atmosphere. Pluto is small enough that its atmosphere actually flows out into space. It can't quite hold on to it. So this is a continual flow of gas away from Pluto, and we had plasma instruments that could measure the solar wind and the effect of that flow on the solar wind. We had radio tracking to measure the atmospheric density by passing radio waves through the atmosphere. And we had one built by students at the University of Colorado that measured dust in the Pluto system. So it's a pretty diverse set of instruments, much more sophisticated than the Voyager spacecraft that flew to the other giant planets was able to carry, because we're 20 years further along in the technology that's available. So it was finished in late 2005. Here it is being unpacked, taking that anti-static wrap off it at Cape Canaveral in their clean room, getting ready for final preparation for launch. Here is the spacecraft is now wrapped in this gold foil, which is in insulation. It keeps the spacecraft warm in the incredibly cold temperatures out there in the outer solar system. It's being lifted on top of the third stage rocket that you can see back here that will actually boost it out of Earth's orbit and send it off towards Pluto. Here it's being enclosed in the nose cone of the rocket that will seal it in there. You can just see it disappearing, and there's the third stage underneath. Here is Alan Stern, actually inside the nose cone. They had to drag him out of there afterwards. But saying a final farewell and good luck to the spacecraft. And here it is now completely encased in the nose cone of the rocket, about to be hoisted up onto the top of this 200-foot tall Atlas V rocket, which was at the time the most powerful rocket that NASA had in its arsenal. And if you look at the spacecraft inside this nose cone, and then look at that here, you can see the spacecraft just a little kind of hood ornament down inside here. So we have a really big rocket and a really small spacecraft being accelerated, and that means you can go really fast. And in fact, this was the fastest ever launched spacecraft ever launched from Earth. Here's a picture of the launch. It passed the moon's orbit in 9 hours. That's how fast we were going. And it was something to see. Here we are watching the launch. This is me in the corner here, looking quite a bit younger. And just, it was like suddenly it was there on the launch pad. We were a long way off, and then suddenly, whoosh, it was gone. And we knew it was safely on its way. Here is an animation of the spacecraft now still on that third stage, which is just fired to boost it up to escape speed, this incredibly high speed, and being released from that rocket and going off on its way towards Pluto. Incidentally, that third stage was going at almost the same speed, and so that's gone off towards Pluto as well, and we have no communication with it. But we can kind of calculate where it is, and it's going within a few million miles of Pluto, I think, no closer than that. Then we had a party afterwards, the favorite part of which was the burning of the contingency plans. I guess this is a tradition for rocket launchers, that when you're launching a rocket, it's a risky business. You have to have all this documentation of what you do if something goes wrong. And So Atlas V mission failure, contingency and accident investigation plan. Didn't need that anymore. So there it went. And something that was pretty cool is here is attached to part of the spacecraft is some of Clyde Tombaug's ashes. So he got to go to the planet he discovered, which is pretty astonishing. And then we left Earth. We crossed the orbit of Mars in a matter of a month or two. And then we headed out towards Jupiter. And it took us only 13 months to get to Jupiter. That's how fast we were going. And we wanted to fly by Jupiter because Jupiter's gravity would give us a boost on our way to Pluto, and it would allow us to speed up and cut some of our flight time off, and it allowed us to get, we'd still be 2 years from Pluto if we hadn't got that boost from Jupiter. So we flew past Jupiter outside the orbits of the big moons. You can see when we flew past, all the moons were hiding on the other side of Jupiter, so we didn't get very close to any of them. But that was okay, because that wasn't the purpose of our going there. We just needed Jupiter's gravity to get us on our way to Pluto. We did take this very cool infrared picture of Jupiter, sorry, not Pluto. And one of my favorite places in the solar system is the volcanic moon Io, and because I was in charge of some of the planning of the observations, I made sure we took lots of pictures of Io. But this shows the different cameras we have. We have this high-resolution black and white camera called LORRI, which takes this image of this is a glowing volcano and a huge plume of volcanic debris being erupted from that volcano. Here is a color camera, which doesn't take such as detailed pictures, but you can see now the red glow of the volcano and the blue canopy of the very fine particles. And this is our infrared instrument, which is measuring the heat radiation from dozens of volcanoes on the night side of Io. So this shows how, looking in these different kind of instruments, you learn different things about the target. And we just took some beautiful pictures too. This is the moon Io with its active volcanoes, and Europa, where NASA just approved a mission to go and look at Europa and study the water ocean, the huge ocean that we think is underneath the ice surface of Europa here. It's a cool place too. And then off we went past the orbit of Saturn and Uranus. We had like a little celebration when we crossed each of these orbits, until finally we got to Pluto in this summer. And so that was a 9.5-year flight. And we were actually pretty busy that period because we had to plan in great detail, well, in perfect detail, everything we were going to do when we got there. So we were glad we had many years to do that. Here's the trajectory looking straight down. It's pretty much a straight line once you get to Jupiter, out to Pluto, and our rendezvous in July 2015. And we'd have a cake every time, the orbit of the anniversary of every launch. So we marked the years as we went by. And so we did a great deal of planning. We actually rehearsed the whole sequence that we developed for the spacecraft, all the pictures it was going to take when it got to Pluto. We rehearsed them on the spacecraft 2 years earlier. So the spacecraft did all the maneuvers and took all the photographs of nothing. But we made sure it could make all those turns and look at everything and download the data and do everything perfectly before we got there. So because we only got one shot at Pluto, you're going at 10 miles a second. You're going through the Pluto system in a few hours. It takes 4.5 hours for a radio signal to get to the spacecraft and 4.5 hours back. So if anything goes wrong, by the time you know about it or could do anything about it, it's too late. So the spacecraft has to do everything automatically and flawlessly, and if you get it wrong, you just can't go back. There's no way of slowing down and going back and having another look. So we really tested everything extremely. And then finally, earlier this year, we started our approach, and we started to put all those plans into a practice, and it was a very exciting time. It was, you can imagine. By June 2015, this seems like a long time ago now, we were getting pictures that looked a little bit better than that fuzzy blob you saw from Hubble, but it's still a fuzzy blob. But by the middle of June, it's starting to show details, and you see some pretty interesting looking things here, but we really had no idea what they were like yet. This is a movie that we made. These are real pictures, and these, I guess, were taken in May. And you can see Charon, the big moon, orbiting around Pluto. And you can, and as you've watched, you can see deep features on Pluto rotating around. We had no idea what any of those things were at this stage, but it was very exciting to see that, and every day it got better. This was one of our first discoveries. This is Charon, and you know, often planets will have polar caps, and polar caps are usually white because they're made of ice, because it's cold at the pole. Makes sense. Here's the polar cap on Charon. It's not white. It's dark. We're still scratching our heads over that one. But even on these pretty early images, which are originally quite blurry, but we were able to sharpen them, you could start seeing pretty interesting and surprising things. And then something that I was involved in a lot was the question of whether it was actually safe to pass through the Pluto system. We had found 4 small moons, and every time we looked, we seemed to find more. So maybe there was just all this debris orbiting around Pluto. Maybe our spacecraft was going to smash into something as we went through the system. So we were concerned about that. And so I was part of a team that was taking a lot of pictures on approach. This is a series of them, and this is just going to repeat. Here you can see the 4 moons we talked about. This is Styx, Nix, Kerberos, and Hydra. And you can see that they're moving in this sequence. This is the real data, not a computer animation. And we were going to fly through the Pluto system about here, on the side of Pluto opposite from the moon Charon. We wanted to know there was no debris around there, no small moons that might be shedding debris. So we took all these images, took about 1,000 pictures, had to process them in real time. So if we found anything, we would be able to divert the spacecraft to another trajectory where it would be safer. And we didn't find any new moons at all. We were a little disappointed about that. We found we have the big moon Charon and then these four small ones. And so that was a bit of a disappointment, but the main thing is we knew there was nothing else that was going to cause a problem for the spacecraft, and we gave NASA the thumbs up. Go ahead, fly the plan that we really want to do, and let's get the best data we possibly can. So here we are. This is the hazard team. Here we are actually searching for things. And here we are celebrating after we were done. And this actually, if you look really closely, this is a Harry Potter magic wand here, which was one of our good luck totems that we used as part of our tools of the trade. So this was in June, and we gave the all clear. And so we were then could focus on Pluto itself. And around July 3rd, things were starting to get kind of weird. This is the best pictures we had then. This is still 11 days before we got to Pluto. You see a string of black dots running along the equator. The North Pole is here. The equator's kind of around here. Very odd looking. We've never seen anything like that on any planet before. So we were getting really psyched for what we were going to see next. And then July 4th, we had a problem. And the spacecraft computer crashed. The guys in the control room were getting the telemetry back from the spacecraft, and then just suddenly it cut out. And that was a very scary moment. Fortunately, I was not in the control room, and by the time I heard there was a problem, they'd waited an hour, and the spacecraft had come back on again and said, okay, I'm having a problem, but I'm dealing with it. Here's some information, which is exactly what the computer was programmed to do if it had a computer crash. And so right away, they were able to start diagnosing the problem. They just overloaded the computer trying to do too many things at once. And this is just a picture of me listening in on a telecon where people are just going through the checklist of all the things they had to do to get the spacecraft back up and running. So by July the 6th, the 6th, just 9 days, I did the math wrong, that's 8 days before closest approach. Things were getting back on the mend. We had a team reception. All the team was gathering at the Applied Physics Lab in Columbia. And yeah, somebody figured out that Wisconsin cheesehead hats are perfect shape to make New Horizons spacecraft hats out of. So this is Alan Stern, our boss, the chief scientist on the mission. And this is the project manager, Glenn Fountain, having some fun there. So it wasn't until July the 7th, only 7 days before Pluto, that the spacecraft was actually back up and running and taking pictures again. So we all breathed a huge sigh of relief at that point. And now the pictures were looking very interesting. And we we realized Pluto was really telling us it loved us and wanted us to come, because there's a heart there. And that was really sweet of it to show us a heart. And then this is now 3 days before closest approach. And it's looking really strange. These are those same black dots that we saw before in those earlier pictures, but now we're seeing a lot more detail. And what the heck is this stuff? And the frustrating thing is we will not know, because remember, Pluto has a 6-day rotation period. So this is 3 days beforehand. So by the time we get close, this part is on the other side. And this is the best pictures we'll ever get of this side of Pluto. So we'll be scratching our heads over this for a while. And then this is 2 days before closest approach. This is the last picture we got before the day of encounter, because then the spacecraft just got really busy. And when it's taking pictures, it can't send data back, because the cameras point one way on the spacecraft and the antenna points the other way, and you just can't point one at the Earth and the other at Pluto at the same time. So for those last couple of days, we knew it was getting closer and closer. The pictures were getting more and more interesting, but we had to be patient for a while. And this is the heart kind of rotating into view again. You can just kind of see Pluto's rotating in this direction. We were heading to get a close-up look at this part at closest approach. And then the last picture we were going to get before encounter day, which was 3 times better than this, that was going to be the first picture where we could really see serious detail, came in about 11 p.m. the night before encounter. And some of us had to stay up all night getting that picture ready for public release the next morning. So here we are at 1 a.m. Or here's some other people on the team, and getting our first look at this picture that was by far the best picture of Pluto anyone had ever seen at this point. It was a very exciting, exhausting night. And finally, by 3:30 a.m., we had the picture ready for a release, and here it is. And now you can start. Now you're really seeing what Pluto is like for the first time. You're seeing it has craters here. So parts of Pluto's surface are pretty old. They've been hit by comets and asteroids, not asteroids, but other objects in the outer solar system over the age of the solar system. But some regions look really smooth down here. So there's some very old stuff, some very young stuff. Makes it very interesting with a lot of variety. So then we went back. I drove back to the hotel, and the birds were singing by the time I got back to the hotel, which is never a good sign. And then we had to be back to work on the data about 2 hours later, so I got very little sleep that night, but it was a very memorable night anyway. And 8 a.m. on encounter day, we were able to release this picture to the world, and it went viral on Instagram, and the president actually retweeted the picture, and it was just crazy that there'd been 5 of us working on this picture overnight, and millions of people saw it the next day. But it was a pretty crazy time. It was a pretty crazy time for the spacecraft as well, because this is all the things it was doing as it was flying past. This is one of our planning diagrams. Here's Pluto, here's Charon, here's the spacecraft going pretty much in a straight line through the system. Each of these colored lines is what it's doing at a particular time. So the blue is where it's taking black and white pictures. The red is where it's taking infrared spectra. The gray is the black and white pictures. Here it was passing through Pluto's shadow and then Charon's shadow to see what the atmospheres were like. So this very complex choreographed procedure. And all this was going on without it talking to the Earth. And we had told NASA, oh, it's perfectly safe. There's no danger of us running into anything. We'll hear from the spacecraft afterwards, don't worry. But some of us are joking about maybe we need to stand near the door when we get the signal back, just in case we don't get it. But we got the signal back, the spacecraft did survive, and it was a very emotional moment when we learned that, yeah, the spacecraft is healthy, it gathered all the data, the data recorders are full, no anomalies, and we all breathed a huge sigh of relief and had a huge celebration, except we were too tired to celebrate very long. So the next day, the spacecraft then could turn its antenna back to the Earth and start sending the data back. And here we are. I happen to be at the controls of this computer in the media room where we were deciding on press releases when the first high-resolution pictures came back. So this was an amazing moment to see not just Pluto as a whole disk, but see fine details on the surface for the first time. And what we're all looking at and being so happy about was a close-up of this little area here. And this is what that picture looked like. And we were just seeing surfaces like something like we'd never seen before. These little bumps here turned out to be mountains about the height of the Wasatch Mountains here. We have no idea what this stuff is. Very smooth areas, and there isn't a single impact crater in this area. We know we saw craters coming in other places, but this part of Pluto has to be very young. Something is repaving this, resurfacing. There's active geology happening here, just as there is on the Earth. The moon is covered in impact craters because the moon is geologically dead. It's just done nothing but got hit by cosmic debris for billions of years. The Earth has a few impact craters, but not very many, because the Earth is alive, constantly destroying craters, replacing them with mountains and deserts and everything else. And so this told us Pluto is alive. There is stuff going on there that is not biologically alive, but geologically alive. So this was a wonderful picture, just that first picture, and then they just keep getting better. Here's now a wider view. That other picture is kind of close up here, but pretty soon we got high-resolution pictures of this whole area, and we discovered this is actually part of Pluto's heart. It's like the left ventricle or something. And this is what it actually is. It's this enormous smooth plain. And we have unofficial names. We don't have official ones yet, but we're calling this Sputnik Planum. And it's like nothing we've ever seen before in the solar system. Here is a close-up view of this corner of it. And look at this stuff. This is really smooth, and it's flowing, whatever this stuff is. You can see it's flowing between these mountains into this bay here. Here it's actually, you can see stuff flowing into a breach in a crater wall and filling the crater floor. And then these things look like, I don't know if you have miso soup in a Japanese restaurant or something, and you look at it and it comes out and it's hot, and you see these little convection bubbles, or just any kind of boiling liquid on a stove will do that. It looks like this nitrogen, we think this is nitrogen, is boiling very slowly, very cold boiling, but it's convecting. Stuff is welling up from below and cooling and falling down again, and making these very distinctive patterns here. So this is a glacier of nitrogen ice, or a sea of nitrogen ice, a boiling sea of nitrogen ice. I mean, who could have imagined such a thing? But there it is. And here's another part of the edge of the heart region here. And when we look at that up close, these are those mountains like we saw before. But you see there's just a whole logjam of mountains here. We don't really know what's going on here, but we think these are floating mountains of ice. You know, ice mountains, the height of the Wasatch Mountains, floating in nitrogen. It turns out that liquid nitrogen, or solid nitrogen, is heavier than water ice, just a little bit. So it can actually flow underneath the ice that we think makes up most of the crust of Pluto, and break off mountain-sized chunks and swirl them around and collect them all in one corner of this ice lake here. And so that's what we think is going on here. We may be wrong, but that's the best idea we have right now. So this is a kind of geology we couldn't have imagined and have never seen before anywhere. Here's another region around Sputnik Planum. And here, it's a little hard to see here, but you can see, I'll show you better in a minute. We're actually seeing flowing of ice down from the highlands here, from these upland lakes, down and spreading out into this pool here. So we have ice flowing into this giant ice sea, ice flowing out of it around the edges here. So very dynamic planet with amazing stuff going on. And then I'm glad I'm giving this talk today, not yesterday, because last Sunday we got down, I think, our most spectacular pictures yet, and they were publicly released this morning, so I can show them to you now. And this is a wide-angle view looking back. This is about 15 minutes after the closest approach. And we're looking back over, this is Sputnik Planum again, that vast nitrogen ice sea. There are the mountains on that we saw in that first image. And here's the atmosphere, Pluto's very thick atmosphere. If you see pictures of the Earth from space, the atmosphere is just a thin blue line along the edge here. But Pluto's atmosphere is very thin, but it's enormous. It goes up hundreds of miles full of haze that we can see in this view. This does not do justice to the full picture, so I'm going to zoom in on just a little bit of it here. And so that whole picture is this level of detail. And it's like you're flying over Antarctica or something, except it's hundreds of degrees colder than Antarctica, and this is frozen nitrogen, not frozen water. It's just fabulous. And so we've been drooling over this picture for about 5 days now, and I'm glad we can share it with everybody now. I think I have time. I'm going to break out of PowerPoint for a minute, and I hope this goes smoothly, but I'm going to go to the full-size live version of this image, and we can just sort of scroll across it and admire all the stuff here. So more weird and wonderful landscapes over here. You see the curvature of the planet. It's starting to bend away. But just incredible detail here. The whole picture is about 5,000 pixels by about 20,000 pixels. We haven't even released all of it yet. And we'll get more pictures of this kind of detail. We'll get a color picture with this level of detail in this weekend, I think. And hopefully we can release that next week. So going back here. So another interesting area is over on this side. These are those glaciers that we saw before. And now, if you see these street flow lines of the glaciers coming down out of the mountains and going around the corner here, it's very much like a terrestrial glacier here. This is a glacier in Alaska that actually doesn't exist anymore, but this is an old picture of these glacial moraines. And so here we see something strikingly familiar in this completely alien landscape. So rampant speculation, but what we think may be happening is nitrogen is evaporating from here when the sun warms the ice, is condensing over here, and then flowing back down into the nitrogen sea as glaciers. So we have a nitrogen cycle, we think, kind of like the hydrological cycle we have here on the Earth, but made of frozen nitrogen. It's all very mind-boggling. And here again, we think maybe the nitrogen is flowing underground. Nitrogen is really soft even at these temperatures. Flowing underground, penetrating cracks, breaking up the crust and causing these mountains to float and assemble in a jumbled logjam here on the edge of the nitrogen sea. So maybe we've got that figured out. There's a lot of stuff we haven't figured out yet. Here's another close-up area with, I don't know what to make of this. It looks like it almost looks like rivers were flowing here, but rivers make no sense at minus 300 degrees. And so we're puzzling ourselves over this, but we'll get better pictures of this region pretty soon, and we're very much looking forward to those. The spacecraft went behind Pluto, watched the sun set behind it. And as the sun set behind it, passed through the atmosphere, and the sunlight passed through the atmosphere, we could measure what the atmosphere was made of from the light that was absorbed by the sun. And then we continued on beyond Pluto, and that was a simulation, of course. This is a real view now, looking back at Pluto. A complete ring. The sun is off in this direction, but the atmosphere is so tall that we see the atmosphere lit up all the way around Pluto, creating an absolutely beautiful ring of haze. And now that ring has got smaller and smaller as we got further away. We go about 1 million miles or 500,000 miles a day, and so we're now 30 million miles beyond Pluto. We're going to turn back in late October to look one last time and look to see if we can see any rings or anything like that. But I'm getting a bit ahead of myself because I haven't talked about the moons yet. I really like this picture. This is a real picture with the correct distance between Charon and Pluto. So here's Charon over here with that dark polar cap that I mentioned earlier. So Pluto kind of stole the show, but Charon is pretty cool too. This is the best picture we have so far. We have much better pictures, but they haven't been sent back from the spacecraft yet. It's going to take a year to get all the pictures back. And we'll get the good ones first. So we'll have much better pictures of Charon in a few weeks. But for now, this is pretty much the best we have, except for some very small areas. So Charon is pretty interesting looking too. There's that dark North Pole that we haven't figured out. Here's a line of faults. You can imagine this is kind of like the Wasatch Front. You've got the line of mountains rising over a plain here, and it may have formed in a similar kind of way by the stretching of the crust and the uplift of the mountains on one side and the filling in of this area with smooth material. Here you see there's lots of craters. So this is a fairly old surface. It's a couple of billion years old, maybe. Charon is probably not active right now, but it has had an interesting geological past. Here is a really odd thing. Here's a mountain in a moat. There's a mountain sticking up, we don't know why, and it's surrounded by this moat, and we don't know why either. And we're really looking forward to getting the better pictures of that. Maybe we'll figure it out. Here are the small moons, Nix and Hydra. They're much smaller. We'll have better pictures soon of Nix. This is about the best picture we're going to get of Hydra because it was on the wrong side of Pluto when we flew past. But we now know the sizes of these. They're about 20 miles across, something like that, 25 miles. They're very bright. They're probably covered in ice. The big red spot on this one that we think is a crater, but we don't know. A red crater is a really weird thing. So we're just getting the highlights of Pluto so far. Only maybe 10% of the data is down yet. And every few days now, we're getting something amazing. This weekend, it'll be this huge color picture. Then we'll be getting some of the really high-resolution pictures in the next couple of months. And it's just an amazing time right now. But we're not done with the mission. We're going on through the Kuiper Belt. Remember, Pluto is one of the largest objects, in fact, the largest object in this vast swarm of objects out beyond Neptune that we call the Kuiper Belt. And when we designed the mission, we wanted to fly past some other object out here in the Kuiper Belt, so we wouldn't just look at Pluto, we'd look at some of these smaller objects as well. The problem is we hadn't discovered any that we could reach yet. We knew there were hundreds of thousands of objects out there, and we knew just from the numbers, there ought to be one along that direction somewhere. But we hadn't actually proved that, and we hadn't actually found that. So starting about 4 years ago, we started applying for a lot of time on big telescopes. We used some of the biggest telescopes in the world, the Magellan telescope in Chile, the Subaru telescope in Hawaii. We spent dozens of nights of the telescope over 4 years, and we found dozens of objects out there in the Kuiper Belt that no one had ever seen before, but none of them were very close enough to our trajectory. We only have enough fuel to bend our trajectory by about ½ a degree. So if we're heading this way and there's a very interesting object over here, we just can't get to it. It has to be almost along our line of trajectory for us to reach it. So we were getting quite concerned about a year and a half ago, I guess it's nearly 2 years ago now, and we decided we need the Hubble telescope to do this job. So we applied for time on Hubble, and we needed a lot of time on Hubble, and Hubble is the premier telescope in the world. It's orbiting the Earth. It's very precious. It was very hard to get that time, but we were actually able to talk them into giving us that time. And we took about 1,000 pictures with Hubble, and Hubble has the clarity of vision that we could find our objects. And here's one of them. You see it like in Clyde Tombaugh day. You can see it's got the green circle around it. And you can just see a faint object moving inside that green circle, and we're just cycling the movie back and forth so you can see it moving. But we were really doing Clyde Tombaugh all over again. We had 1,000 pictures. We were looking for things that faint among millions of background stars. But unlike Clyde Tombaugh, we had computers to help us. And a computer spotted this, and we were able to confirm that it was real. And this object is actually the one that we have now chosen to go to. We found 2 objects that we could reach. And we decided we liked this one better. It didn't take as much fuel. So in October, we stopped taking data. We stopped sending down data for a couple of weeks. We prepared the spacecraft, fired the engines to set our course towards this object. And here is a rather more accurate view of the Kuiper Belt. Here was Pluto and our trajectory past it. This object is the one labeled with the yellow arrow there that we're going to reach in January 2000. Actually, it's on New Year's Day, early on New Year's Day 2019. For a long time, we knew within a few hours when we were going to get there, but we didn't know which year we would get there because it's right at New Year's. Anyway, that's when we will get there, and we have now 3 years to figure out all the observations we're going to make when we fly past that object. And it currently has this very glamorous name. We'll probably have a naming contest to find a better name for it, but this is its current temporary designation. So January the 1st, 2019, we will fly past one last world and learn about these smaller objects out in the Kuiper Belt. And then we just continue on into interstellar space. We'll be able to talk to the spacecraft for another 15 years, maybe into the mid-2030s. Then the power supply will die to the point where we just won't be able to communicate with the spacecraft anymore. But it's going to keep going and carrying Clyde Tombaugh's ashes out into the galaxy, which is a pretty cool way to end the mission, I think. So thank you. Yes, I'd love to answer questions if people have questions.
John is happy to entertain questions.
Yes.
What's the data rate coming back from the spacecraft?
It's about 1,000 bits per second, maybe 2,000 bits per second. So it's kind of dial-up speeds. And we have gigabits of data on the spacecraft. We have, I think, about 50 gigabits, something like that. So that's why it will take a year to get all the data down. But because we can prioritize it, we're obviously prioritizing the closest, best pictures first. And so I think by Christmas, or maybe early next year, we'll have most of the really good stuff. And then we'll get all the other more distant pictures or pictures of empty space that might have something interesting in them later. And we may find cool stuff in there too, but we'll be right now, we're in the middle of getting the best stuff down, so this is a really exciting time. We're writing papers, or we'll be submitting papers to Science magazine in the next couple of months. We're presenting the first results at conferences, so yeah. Yeah.
Would you like to speculate on what that belly button-like feature is? That strange thing that seems to be...
Let's see, which one are we? This on Hydra?
No, on Pluto.
On Pluto. Oh, the mountain in the moat. Yes, that's... No. Okay, we don't know what that is. Okay, tell me when to stop.
Keep going. That. Just past it.
Okay.
That.
So this thing here?
Yeah.
Yeah, we've been wondering about that. It's this whole terrain is really baffling. In fact, we were arguing about it yesterday. Some people think it's produced by tectonic forces, that the surface has been squeezed and mountains have been uplifted here. To me, it looks more like a vast pile of dust bunnies, and we really don't know. And this hole may be telling us something about what's going on there. If I do go forward to, oh no, I don't have it here, but this is that same hole backlit, so we have another view of it now. It's a weird feature in the middle of weird features, and that's as much as we can say right now. But we will, what we'll be getting soon is the images of these things from different angles, which will give us stereo, which will allow us to make very accurate topographic maps of the surface, and I think that will help us understand. Let's see, there's one right at the back there.
Yes, you said Pluto's atmosphere continually flows away in small amounts out in space. Does that imply that Pluto's nitrogen is limited and these forces that we see with its nitrogen cycle will eventually stop?
That is a very good point. In fact, that's something we were puzzling about beforehand. We think over the age of the solar system, at the current rate of escape, Pluto might have lost about 1 kilometer of nitrogen. Maybe half a kilometer, something like that. A pretty substantial amount. So we wondered, where's that nitrogen coming from? Now we see this enormous lake of frozen nitrogen, and this is a reservoir of nitrogen that will probably last a couple of billion more years, even given this escape rate. And so we suspect that this is why it still has an atmosphere and it hasn't all gone yet, because there's this enormous nitrogen reservoir that can continually evaporate and supply the atmosphere. Yeah, let's see. Okay, yeah, there. That's a really good question. Everything we see on the surface is ice, either water ice, like the stuff you'd find in a refrigerator, or these more exotic ices, nitrogen, methane, carbon monoxide, which are gases on Earth, but it's so cold on Pluto they freeze out as ice. But we know there's rock there too, and the reason we know there's rock there too is because we know how much Pluto weighs. And if it was purely made of ice, it wouldn't weigh as much as it does. And so there has to be rock in there as well that's heavier than ice. And what we think probably that Pluto got heated early on, perhaps when it had this giant impact that produced the moon, and all the rock sank to the middle. So we think there's a ball of rock in the middle, and then a thick layer of ice, water ice, ordinary ice, and then all these other exotic ices on the outside. But we'll be looking with our infrared instrument. If there is a rock on the surface, we might be able to see it. I don't think we will, but we're going to look really hard for stuff like that. So yeah, great question. And back there.
Do you think that other objects in the Kuiper belt would look similar, this sort of nitrogen ice, or do you think they'd be completely different from Pluto?
I think the biggest ones, like Eris, which is about the size of Pluto, probably looks a little bit like Pluto. We'd love to know, but it's too far away for us to send a spacecraft to right now. But the objects we're going to are much smaller. They are more like asteroid size. The one we're going to get closest to is going to be about, we think about 20 miles across, something like that. So it's a much smaller object, probably quite dark, though we don't know that yet. And we don't know what it's going to look like, but it's probably too small to hang on to nitrogen. Even Pluto can barely hang on to its nitrogen. And this object has probably lost its nitrogen, though it would have had it sometimes. It will have some other kind of surface. We don't know what yet. We can't wait to find out. Yeah.
I understand that there are several objects in the outer solar system, satellites that have substantial surface area that's coated with hydrocarbons, most notably Ionis,
Right.
Saturn's moon. Is it possible or probable that the dark features on Pluto and its moons are like that?
Yeah, that's our best guess, in fact, that there's methane in the atmosphere, and ultraviolet light is acting on that methane and breaking up the methane molecules, and which then recombine into larger molecules. We know there's ethane there. And that process will probably continue until you get pretty complex hydrocarbons, which then are not gases anymore. They settle out on the surface. Maybe they get blown around by the winds. We don't really understand what happens. Somehow they all seem to end up at the equator. So they have this band of black stuff, and it's probably hydrocarbons, maybe with some nitrogen as well. But we haven't got the good spectra yet, and it's a little hard to tell hydrocarbons from the spectra, those kind of tarry things. But that's our best guess at the moment, and we've got a lot more data coming down that may help us to figure that out. Yes, over here.
Do you have a website where we can find out what's
Oh, yeah. If you just Google NASA, Pluto, or New Horizons, it's pretty easy to find. It's actually pluto.jhuapl.edu. It's Johns Hopkins University Applied Physics Lab. So that's the address, but we're pretty easy to find on Google at the moment.
in the depression that was in question there.
Mm-hmm.
Some of the features around there look like grottos in southern Utah,
Yeah.
which are slot canyons that the bottoms dropped out of.
Mm-hmm. Yeah, let me see if I don't have a really good, this is about the best view I have, but these look like grabens here. Yeah. We're pretty sure there. We do have better pictures, I just don't happen to have them up here. But yeah, that seems to be exactly what's going on there. Yeah. Yeah, over here.
When will New Horizons exit the heliosphere, and because it's a newer spacecraft, will we get better data than the Voyager?
Wow, that's another very good question. The heliosphere is the bubble in interstellar space that's blown by the solar wind. The sun is a little bit like Pluto in that the sun can't hold onto its atmosphere either. So though for different reasons, so the sun is continually pouring gas out into space, and that forms this huge bubble that extends out 100 times further from the sun than we are. And that's the heliosphere. And the Voyager spacecraft that flew past the planets in the 1980s, the giant planets, and we're still talking to, astonishingly, recently passed through the edge of the heliosphere and out into interstellar space. which was a pretty exciting result from that mission. We probably won't last quite as long as the Voyager spacecraft. We don't have as much plutonium, which is what powers our spacecraft. And so probably we won't make it quite that far. But we're not sure yet. We might find ways to save energy and continue out that far. And we have instruments that can measure that. And even if we don't get out into interstellar space, we'll be able to measure what the heliosphere is like out in those outer reaches, the furthest reaches of the solar wind, with a lot more precision than the Voyagers were, because we have instruments that are 20 years more sophisticated. And so I think there'll be very interesting stuff to learn out there too. Yeah.
How much, you talked about the spacecraft going into the shadow behind the planet as well as its moon.
Mm-hmm.
And how much information have you received back that tells us about what that atmosphere is you might have captured? I know you've been focusing on photographs.
Right.
Mm-hmm. How much processing have you gotten?
We're starting to get those data back. We got a sneak peek early on that showed that, yeah, we saw a very strong signal of the sunlight being absorbed by the atmosphere. And we measured the radio waves being slowed down by the atmosphere as well. And so we measured the pressure at the surface, and it's about where we expected, except that observations by looking at stars going behind Pluto show about twice as dense an atmosphere, so we're puzzling over that at the moment. It's about 10 millibars is 10 microbars is the pressure. We haven't learned so much about the composition yet because those data have not, I think they're coming down in the next couple of weeks, and I'm not so involved with that part of it, but I will be very interested to hear what they find. But we don't have, we only have hints right now, and we'll get the good stuff very soon from that experiment. And yeah, there's someone behind you.
Also in the atmosphere, on the newest image that we received, the public received today, there are very clear separations in the atmosphere,
Mm-hmm.
dark sections. Do you speculate whether or not those are different chemicals, or if they are just different layers of nitrogen as it's escaping?
What we think here are some of the hydrocarbons that are forming from ultraviolet light acting on the methane in the atmosphere. We can't see the gas. The gas is too thin to see. So what we're seeing is very fine, tiny particles of hydrocarbons being formed in the atmosphere, and then they will slowly settle out. And so the fact that they have this incredibly complex structure, and it's not the same everywhere. If you, like this area is very strongly, very clear layers. That area, not very many layers at all. So there's a lot of variation. And we're going to be very interested in how those layers change. We can maybe actually see motion in those layers. There's, I don't know if you can see it here, but there's, no, it's a little hard to see, but over here there's just a little tiny, almost like a discrete cloud of a Sputnik planum. So we think it's something to do with how the winds are flowing in the atmosphere, how the particles are settling out, but we sure don't understand it yet. But we're looking forward to trying. Yeah. Well, fortunately, it was NASA's job to ask those hard questions first, and we had to have answers ready. So all the things that, they asked a lot, they spent a whole day, well, grilling the engineers, not me particularly, but the engineers, how do you know that you won't have crosstalk between these components, or how are you going to maintain the voltages, and how do you know that this instrument is going to be able to measure what you think it's going to measure? We had to have something that was really bulletproof in order to get the proposal accepted. And so we were pretty confident. I think the scariest thing was the time scale. In order to catch that ride from Jupiter, we had to launch in 2006. And the proposal, the beginning of 2006, and it was the end of 2001 when we got the go-ahead. So we basically had 4 years from 2001 to 2005 in which we had to work out all those details and actually build this thing and get the nuclear launch approval and get all the instruments working. And so the time scale was the challenging thing. We knew we could do it, and we certainly had prove to NASA's satisfaction that we could do it in time, but I think that's the thing we were most nervous about, is that we could really do it in time. Yeah.
Going along those lines, were there other groups that didn't get their proposals accepted that then gave input to you? Did you interact with any of them?
We did a little bit. We invited some of those people onto our team because a problem with this is that one of these opportunities come up, and the best people sort of divide into different groups, and then one of them gets lucky, and so some of the best people get left out. And so some of those people we invited to join, I think one or two of them did. Most of them had other projects to do because they're the best people and had plenty else to do. But we did interact with them, but not in a lot of detail. A lot of them showed up for the encounter, actually. And they were very good sports about that, and were as excited as we were that somebody got to fly that mission and got to see all these amazing things. Yeah. Oh.
Where does all the nitrogen come from? Why did it collect there? Do you have an explanation?
Well,
how plentiful is it in the universe?
Nitrogen is fairly plentiful. There's quite a lot of it in stars. There's a lot less of it than there is of oxygen, I think. I might make a fool of myself here because I'm not a geochemist. But water is very common frozen water is very common in the solar system. There's a lot of that, but nitrogen is also not that rare. We see nitrogen in the atmosphere of Titan and so on. So Pluto just gathered some of it in the process of its formation.
We have a very young
Yes.
astronomer over here.
Yes.
What is the heart?
Well, we think part of the heart is this vast sea of nitrogen. And let me find a good picture of the heart. There we are. So here's the heart. There's one side. Here's the other side. You see, one side is really sharp and easy to see, and that we think is this huge sea of nitrogen. And the other side is not as easy to see. We think it may be where snow has fallen, nitrogen snow has fallen on the ground to the east of that region. So we think that makes the other side of the heart. Incidentally, we call this whole region Tombaugh Regio after Clyde Tombaugh, who discovered Pluto. It's the largest and most impressive feature on Pluto, so we named it after him. But yeah, we sort of think we know what's going on here. We don't really know what's going on here. We're still working on it. But those are the two halves of the heart.
So I think we should call it quits now. But let's thank John Spencer once again.